So let's take a look at applying Dijkstra's. Oof, that's a hard word to say. Uh, the Dijkstra algorithm um, in a grid-based setting. So I've got this map. It's like a Dungeons and Dragons map, and let's suppose in this fantasy world that we've got a robot that is moving these barrels over here, and that's going to be for some sort of party or something to have them around. And so, if we want to apply that algorithm, the first thing that we need to do is the robot would actually sweep through and find out where all the collisions are. So let's kind of simulate what that would be like. The first thing it's going to do is it's going to it's going to find these barrels here. Maybe we'll say those are the collisions right there, and we'll just overlay them with black. And now we've got the bar here, and this is a big collision, so we'll black that out. This table here is a collision. Looks like that stool's a collision. So we're just kind of rounding out anywhere that there are objects in the majority of that grid, then we're going to call it a collision. So we're going to say that's a collision right there as well. And maybe this is a collision here. And then we might as well get our walls as well, just so we kind of constrain this whole operation. So here's our walls. Oh. And almost there. Cool. So now this is the space that we have to work in, and we said that we were going to start right here. So let's make an S there, and we'll call that our starting point. And that's actually kind of hard to see. So let's fill the rest of these in with some white, just so we can see what the heck's going on now. We'll fill it in with white, white, white. So what we're doing is we're kind of removing all this visual stuff, because really what the robot's going to see if it's using this algorithm is just space I can travel versus space I can't travel. And so this is kind of an array that it's built. So we're saying that we're starting here and we're going to finish here. And last but not least, let's up my font maybe a little bit here. That's better. So our robot can only move in the orthogonal direction, so up, down, left, right. And what we want to do is we just kind of want to start measuring the distance of the next cell. So that means, let me change my color here to maybe blue. That means this cell is one hop away. Oops, I didn't change my color apparently. Either way, one hop away, one hop away. There's our blue. It's going to bug me now. And this is 2 hops away. I don't know what's going on with the colors. Anyway, 2 hops away, 2 hops away. Then from either of these, this becomes 3 hops away. And then we're kind of narrowed down this channel. So 4, 5, 6, 7, 8, 9, and then it opens back up. So this is a 10. This is also a 10. And then from these 10 spaces, we have 11. 11 for both of these guys, and 11 there. And let's real quick do 12, 13. Then here's another 12. Here's another 12. Here's another 12. Here's a 13. Here's a 13. Here's a 13. 14. 14. 14. 15. 15. 15. Oops. Sorry, that's a 16 there, my bad. And then we're channeled down here again, so we're at 16, 17, 18, and we've got a few 19s around here. So that's 19, that's 19, that's 19. Then we go around these 19s, so that's 20, 20, 20. And now we go off where the 20s are at, so there's a 21, 21, 21. Then off of the 21s, we have our 22s, 22, 22. Then off of our 22s, we have 23s, 23, 23. And off of our 23s, we have a 24. And then the very final thing that we checked is our F here. So in this case specifically, we ended at our final position after we've checked all the cells. But normally the condition is once you've reached this final position, your F or your destination, that's when we can immediately stop and then go back and find out what our route is. So, but it just so happened in this case that we'd already looked at every single cell before we got to this spot. So now that we've found our final spot, we were able to arrive there in this algorithm, we can go back and figure out what route we can take, or define what the route is. So what we do is we just start from our destination, which is F here, and we find the lowest number by it. So remember, we're going orthogonally. So it looks like I'm going to change blue is going to become my path. And now we need to find the lowest number next to this 24, which can be this 23 or this 23. So that's where it kind of comes down to, you have to, in your algorithm, make a decision on how you break these ties. In which case, I'm always going to say it's the most upper left one. So it's going to be this guy here. And most upper left, it could either be this 22 or this 22, but it needs to be that one. And then we got to go down. So 21, 20, 19, and we're just going to keep shooting straight down. In fact, we're going to go down 15, 14, 13. Oops, I said it was going to be the most upper left one. So really it would be this one here, then 13, 12, 11, 10. Then it's going to push us down 3, and most upper left is this guy, 2, 1. So let's get this guy out of here. Red. So this blue part is the path that we found from our start to our destination. It seems pretty simple. This algorithm seems pretty simple, and that's because it is. It's a simple algorithm that works every time. The more difficult part is building this collision matrix, or figuring out where our collisions are. But that's something that we'll discuss in a later video.